There's a reaction sitting inside your kitchen right now that the $184 billion residential heating industry does not want you to understand. 2 ingredients. Both of them are already in your home. Table salt, the kind you shake on your eggs every morning, and aluminum foil, the stuff you use to wrap leftovers before they go in the fridge. Under the right conditions, those 2 things produce genuine, measurable, sustained heat without a flame, without a gas line, without a power outlet, and without a single moving part. The United States military figured this out. They built it into every combat ration issued to every soldier deployed since 1990. They confirmed in laboratory testing that salt is the essential trigger that converts a passive sheet of metal into a heat-generating device capable of raising a meal's temperature by 100 degrees Fahrenheit in under 12 minutes. And then, when the war was over and the contracts were written and the heating industry had its margins locked in, that knowledge stayed exactly where it was. In a military specification document, off the shelf, out of your hands. This is not folklore. The chemistry is documented, peer-reviewed, and repeatedly confirmed across more than a century of material science. The suppression is not a dramatic conspiracy. It is something quieter and more effective than that. It is just the natural result of a market that cannot monetize simplicity. When the answer costs less than $1 and fits in a drawer next to the dish towels, no corporation has an incentive to hand it to you. So they do not. And most people never ask. You are about to ask. Let us start with aluminum itself, because most people do not realize what they are holding when they pull a sheet of foil off the roll. Aluminum is one of the most chemically reactive metals on the periodic table. In its raw state, in a pure environment with nothing protecting it, aluminum does not just corrode the way iron does. It burns. The oxidation of aluminum with water releases at least 270 kilojoules of heat per mole. That is an enormous amount of energy for a reaction that requires nothing but the metal and water to proceed. The theoretical maximum, when aluminum reacts fully with water, releases closer to 1,700 kilojoules per mole. To put that in terms your body understands, that is enough to raise the temperature of a cup of water from freezing to boiling more than 3 times over, from a single mole of aluminum the size of a golf ball. So why is your kitchen foil not bursting into heat every time you rinse it under the tap? Because aluminum has a secret. The moment aluminum is exposed to oxygen in the air, it forms a protective skin on its own surface. That skin is aluminum oxide, and it is only a few nanometers thick. A nanometer is 1/1000th of a meter. The layer is invisible to the naked eye and weighs almost nothing. But it is structurally so dense and chemically so stable that it acts as a perfect barrier between the reactive aluminum underneath and the water or oxygen outside. That thin, invisible film is the only thing standing between your roll of kitchen foil and the production of real sustained heat. And salt dissolves it. Not immediately, not violently, but with precision. The chloride ions in sodium chloride, which is table salt, are uniquely aggressive toward aluminum oxide. When salt water contacts aluminum foil, those chloride ions begin penetrating the oxide layer at microscopic weak points. Once they reach the bare aluminum underneath, they disrupt the surface in a way that prevents the oxide from reforming. The protection is stripped away and kept stripped away. And the underlying aluminum, hungry to react, begins interacting with water directly. The exothermic reaction begins. Heat flows, gas is produced, the temperature rises. This chemistry does not sit in a theoretical paper somewhere. It has been tested under the most demanding real-world conditions imaginable. In 1973, the United States Army Natick Research and Development Center in Natick, Massachusetts, began investigating chemical methods of heating combat rations without open flame. The requirement was specific. Raise the temperature of an 8-ounce meal entree by 100 degrees Fahrenheit in 12 minutes. No visible flame, no electricity, no fuel canister. Just a chemical reaction that a soldier could trigger in the field with nothing but a small amount of water. After years of testing and development, the Army landed on a mixture of finely powdered magnesium and iron with table salt as the activating agent. When water was added and the salt dissolved into an electrolyte, it turned every particle of magnesium and iron into a miniature galvanic cell. Thousands of tiny short-circuited reactions firing simultaneously, flooding the system with heat. The Army called this process, in their patent filings, supercorroding galvanic cells. The salt was not incidental. The salt was the mechanism. That device, the flameless ration heater, was first issued to soldiers in May of 1990 and became standard equipment in every meal ready to eat beginning in 1993. It has been deployed in every major American military operation since. Desert Storm, Somalia, the Balkans, Afghanistan, Iraq, every theater, every climate, every condition. The same core chemistry. Salt triggering a metal's exothermic reaction with water to produce heat on demand, without fire, without fuel, and without any connection to a power grid. And it never made it onto a store shelf as a consumer product. Think about that for a moment. The most battle-tested flameless heating technology in the history of the United States military documented in open procurement records and available in declassified research, has been actively used by American soldiers for more than 30 years. And the average American household has no idea it exists and no commercially available product that replicates it. Because the same technology that heats a soldier's meal in a foxhole could heat a room in a blackout, warm a person stranded in a car in winter, or keep an elderly person from hypothermia during a grid failure. And none of those applications require anything from a gas company, a utility, or an HVAC technician. The residential heating equipment market was valued at $184.5 billion in 2024. Gas furnaces, boilers, heat pumps, electric baseboard systems, radiant floor systems, all of it built around one fundamental premise, that you need an external metered billed energy source to stay warm. You need the pipe running under the street. You need the meter on the side of the house. You need the truck to come fill the tank. You need the technician to service the system every year. You need the contract, the plan, the bill, the renewal, and the rate increase every single year for the rest of your life. A packet of salt and a roll of aluminum foil does not fit anywhere in that business model. So it disappears, not by order, not by law, just by the quiet, efficient arithmetic of what gets funded, what gets shelved, and what gets handed to you in a box at the checkout line. Now let us go further back, because this knowledge is older than the military specification that finally formalized it. Aluminum foil became commercially available around 1910 and 1912, when production methods advanced to the point where it could be manufactured thin enough and cheap enough for everyday use. Within a decade of commercial foil entering homes and workshops, chemists working in the early electrochemistry tradition had already documented the chloride-aluminum reaction in detail. They understood that salt, specifically the chloride component, was uniquely capable of disrupting aluminum's passive oxide barrier in a way that other salts and compounds could not. Halide ions were known aggressors against passive metals. This was not an accident of nature. It was a predictable consequence of electrochemical theory that was being mapped and published in scientific journals on both sides of the Atlantic. But that knowledge moved in one direction, into industrial applications, into military specifications, into laboratory literature. It never moved into household awareness. It never appeared in a magazine column on emergency preparedness. It never made it into a survival manual, a camping guide, or a basic first aid primer. Not because it was dangerous, not because it was difficult, because it was free, because the raw materials were already in the kitchen, because nobody was going to make $184 billion a year teaching you to use them. So here is what you actually need to know. The salt and aluminum reaction, in its most accessible form, does not require powdered magnesium or specialized military-grade iron. The fundamental mechanism, the chloride ion stripping the oxide barrier from aluminum and triggering an exothermic reaction with water, works with materials you already own. Understanding how to build a working version of this takes roughly 20 minutes and costs nothing beyond what is already in your kitchen or can be found for less than $1. You will need aluminum foil, the heavy-duty variety if you have it. You will need table salt, a generous amount, not a pinch, but several tablespoons. You will need hot water, as close to boiling as you can get it. And you will need an insulating container, a wide-mouth thermos, a double-walled cup, or even a pot lined with a folded cloth. Start by crumpling your aluminum foil into a dense, loosely packed ball roughly the size of a fist. You want maximum surface area exposed, which means crumpled and irregular rather than smooth and flat. A smooth, flat sheet has far less reactive surface contacting the water. The more crinkled, folded, and irregular your foil ball, the more aluminum surface the salted water can reach. Dissolve your salt into the hottest water available to you. A saturated saltwater solution, which means as much salt as the water can hold, is ideal. Stir until no more salt will dissolve. The concentration matters because the chloride ion concentration directly determines how aggressively the oxide layer is attacked. Dilute salt water will produce some reaction. A fully saturated solution produces meaningfully more. Pour the saturated salt solution over the aluminum foil in your insulating container. You will notice the foil beginning to react almost immediately. A fine fizzing begins at the surface. This is hydrogen gas being released as a byproduct of the aluminum-water reaction, the same byproduct documented in military FRH specifications and in academic papers on the subject. The container will begin to warm. Within 5 to 8 minutes in a well-insulated container, you will have a reliable heat source that will remain warm for 30 to 45 minutes, longer in a better insulated vessel. This is not a campfire. It is not a furnace. Let us be completely honest about what it is and what it is not. The temperature ceiling of a salt aluminum system using kitchen foil and table salt tops out well below boiling. You're not cooking a roast. You're not heating a house. What you're generating is consistent, sustained warmth, body temperature warmth, the kind of warmth that keeps hands from going numb in a car stranded in a winter storm, the kind of warmth that prevents hypothermia when the grid goes down and the thermostat goes dark, the kind of warmth that heats a cup of water to drinking temperature, warms a cloth that goes against a sick child's chest, or keeps a person's core temperature from dropping into danger. The military specification required 100 degrees Fahrenheit rise in 12 minutes for food-grade applications. That was with optimized powdered alloys and engineered concentrations. The kitchen version operates more gently, but operates on the same verified principle. And in the scenarios where you actually need it most, a power outage, a car breakdown in January, a shelter situation, that gentle sustained warmth is not a novelty. It is the difference between being cold and being in danger. There are further refinements that dramatically improve performance. Aluminum surface area is the primary variable you can control with kitchen materials. Instead of a single foil ball, try layering torn strips of foil in a container, creating a structure with more total surface exposed to the solution. Rotating or stirring the foil periodically introduces fresh salted water to surfaces where hydrogen buildup may have slowed the reaction. Replacing the solution halfway through with fresh saturated salt water restarts the reaction at full intensity. Each of these adjustments is documented as an efficiency factor in the broader literature on galvanic corrosion and salt aluminum electrochemical systems. For extended applications, the reaction can be sustained longer by using multiple foil sections sequentially, replacing spent foil with fresh material as the first section is consumed. The salt solution itself does not deplete in the same way the foil does. A batch of saturated salt water can drive multiple cycles of foil. In a survival scenario where you have access to salt, whether from pantry stock, a camping kit, or even collected seawater that has been evaporated and concentrated, and you have access to aluminum, which includes beverage cans, food packaging, foil rolls, and countless other common items, you have access to an indefinitely repeatable heat source with no fuel cost, no moving parts, and no dependency on any external system. Now, look at that again through the lens of who loses money when you understand this. The gas furnace industry in the United States alone represents billions in annual revenue, with the broader residential heating equipment market sitting at $184.5 billion globally as of 2024. Every household that understands how to generate emergency heat without the grid, without the pipeline, without the tank, is a household that is slightly less captive to that system. Not because you are going to heat your home with foil and salt full time, you are not. But because the narrative that you are helpless without an expensive metered energy source, that warmth is something that only licensed build infrastructure can provide, cracks a little whenever someone learns that two kitchen staples can produce measurable heat on the same principle that the United States military has trusted for over 3 decades. That narrative is worth billions of dollars a year to maintain. Campaigns, lobbyists, industry associations, building codes written to mandate approved heating systems, permitting processes that require licensed professionals, warranties that void if you deviate from approved methods. All of it works together not to keep you safe, which is the official reason, but to keep you dependent, which is the actual outcome. The HVAC technician who charges $300 for a service call knows his furnace better than you do. That expertise is real, but the expertise exists in the context of a system designed so that you cannot function without it. Every piece of that system, from the utility connection to the annual maintenance contract, assumes that you have no meaningful alternative. Teaching people that heat itself, the thermal energy to survive a cold night, can be derived from chemistry they already own is not on the curriculum that system once delivered. The research exists. The military applications are documented. The patents are either expired or irrelevant to the underlying natural chemistry. You cannot patent the chloride ion disruption of an aluminum oxide layer. You cannot patent the exothermic oxidation of aluminum in water. These are laws of electrochemistry, as fundamental as the periodic table they emerge from. Any intellectual property around specific alloy ratios, specific concentrations, specific delivery mechanisms, expired or sits behind corporate walls. The underlying principle is yours. It has been yours since aluminum foil first appeared in kitchens over 100 years ago. It was just never handed to you. Now it has been. Consider what happened with one of the most adjacent technologies to this, the reusable sodium acetate heat pack. Sodium acetate is a salt compound produced by combining vinegar and baking soda. When dissolved in water at high concentration and then allowed to cool without crystallizing, it becomes what chemists call a supersaturated solution. It holds more dissolved salt than it should at room temperature, staying liquid, storing the latent energy of crystallization like a spring that has been wound tight. Snap the small metal disc inside the pack, and the vibration seeds the crystallization. The solution locks into a solid crystal structure in seconds and releases all that stored energy as heat, warming the pack to around 130 degrees Fahrenheit. Completely safe, completely non-toxic, reusable indefinitely by dropping the solidified pack in boiling water and letting it liquefy again. That technology has been documented since the late 1970s. It is sold today in pharmacy gift sections as a novelty hand warmer, not as emergency heat, not as an off-grid survival tool, a novelty because the packaging and the retail placement determine how you conceptualize a tool, and nobody in the heating industry is going to help you see a $4 reusable heat pack as an alternative to a $3,000 furnace replacement. The chemistry is the same. The framing is everything. The salt-aluminum reaction sits in the same category. The chemistry is verified, military tested, and freely available. The framing is what is missing, and that framing gap is not accidental. The practical kit you build from this knowledge weighs almost nothing. A roll of heavy-duty aluminum foil, a small bag of table salt, a wide-mouthed insulated container. The total cost is under $3. It fits in a glove compartment, a camping day pack, a bottom shelf of a pantry emergency kit. It requires no batteries, no power source, no ignition, no fuel. It generates heat from a chemical reaction that every material scientist understands, and that the United States Army spent 2 decades optimizing before quietly keeping it inside a military specification. You're not going to read about this in the camping gear catalog. It will not come up in the HVSC sales pitch. It will not appear in the emergency preparedness guide that the utility company sends to new customers. Those documents are written by and for a system that profits from your not knowing it. The knowledge persists anyway, in military research archives, in electrochemistry literature, in the same basic science that your first-year chemistry professor would confirm if you asked. The system made sure you were not likely to ask. If this kind of information matters to you, the best thing you can do is share it with someone who needs it before the next time the power goes out and the temperature drops, and everyone wishes they had known something the military has trusted for 30 years. Subscribe so you do not miss the next one. What gets buried stays buried until someone decides to dig.